Okay, we're going to talk about H9J diagonal. This is a mouthful. Diagonalization and powers of a matrix. So prior to doing this, it's quite important that you've practiced finding eigenvalues and eigenvectors, which is in the H9I handout. So at this point, you should be somewhat comfortable with eigenvectors and eigenvalues. So this briefly describes what we're doing. So we're only working with a 2 by 2 matrix in this class, in this course. And when you've got a 2 by 2 matrix, if you're going to write a diagonal matrix, basically have a number here and a number here diagonally, and then these would be 0. Okay, and so in your square matrix, if it's diagonal, if you've got a matrix that is diagonalizable for matrix P, then the we can say that P diagonalizes A. So we're going to be using this relationship that we see here, where this is the transformation matrix, and we're going to be finding out what the diagonalized matrix here is, and what is the special name for this? The this is the matrix that is going to involve the vectors, and I'll show that in just a minute. Now, in the formula packet, they don't use the letter X here. They use the letter P here. So just, I want you to be aware, I'm going to be sometimes going back and forth between the letter P and the letter X. In Professor Dave's Explains video, he uses a capital X here, and I'm going to use that a little bit too. So, anyways, so if I've got my if I've calculated my eigenvalues, then when I'm calculating my eigenvalues in my diagonal matrix, each eigenvalue, one of them is going to be here and the other is going to be here to make a diagonal pattern. The eigenvectors are going to be used to find our matrix P. That's this guy right here, P. And and basically our eigenvectors, you're going to put one vector and then another vector. This line here, I only saw this line in the video with the Revision Village people. They put this line here. So basically, we've got an eigenvector it's a 2 by 1 matrix, and there's two of them together, which makes a 2 by 2. Anyways, let's do an example with some numbers. But before we go, you may want to color it in this pattern. I used pink for my diagonal matrix and blue for my eigenvector vectors. And so so this here corresponds with the first one here. Okay, you have to keep them in the order that they're done. And so let's look at an example. Okay. Okay. So okay, so this first question is, before we can even get started, we need to find our eigenvalue. So we're going to show that the eigenvalue is 1 and 2. So and using this relationship, so A is -3, -4, 5, and 6, and minus lambda 0, 0, lambda, and we're going to make the determinant of that equal to 0. So if I write this as a single matrix, I have negative 3 minus lambda, and here I've got negative 4, and here I've got 5, and here I've got 6 minus lambda. Okay, and we're going to make this the determinant of that equal to 0. So if I find the determinant, equal to 0, so then I'm going to have negative 3 minus lambda times 6 minus lambda, right? This guy times that guy, minus 5 times negative 4 equals 0. Simplify this, I get negative 18 plus 3 lambda minus 6 lambda plus lambda squared, and negative 5 times negative 4 plus 20 equals 0. Okay, combine the like terms. I get lambda squared minus 3 lambda plus 2, and then that equals 0. And so we factor that out, and we get lambda minus 1 times lambda minus 2 equals 0. And so that makes it so that lambda equals 1 and lambda equals 2. There, we just showed them. Okay, and now so I'm going to call this, put a subscript 1 and a subscript 2, because it's going to be important to identify which eigenvalue goes with which eigenvector. So with the eigenvalue of 1, we're going to figure out the eigenvector for that. So we've got matrix A, which is negative 3, 4, 5, and 6, minus, and instead of putting lambda in here, I'm going to put in a 1, so 1, 0, 0, 1, because I'm putting 1 instead of lambda. And we know that this is equal to 0, and this will give me the eigenvector for the eigenvalue of 1. Okay, so now I can simplify this. Negative 3 minus 1 is going to give me negative 4. 4 minus 0, that's just 4. 5 minus 0, that's just 5. And 6 minus 1 is 5. Okay. X, y equals 0, 0. Okay, so going from this line to this line looks slightly different than how Professor Dave did it, but we still get the same answer. And so from this here, he did some stuff with reduced row echelon form, but you don't really need to do that in order to solve for x and y. So if I multiply this times this, so for the first row I have negative 4 times x plus 4 times y, and that's going to give me 0. I could do the other row, which would be 5 times x plus 5 times y equals 0. But those two equations are the same, so I don't need to do that. So if I rearrange this, I can add 4x on both sides. I get 4y equals 4x if I add 4x on both sides. And then if I divide both sides... Oh, wait, did I make a mistake? I did. Dun, 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 dun. Notice this is negative 4. Oopsies. Okay, so this should be negative 4. This should be negative 4. And that should be negative. And this should be negative. And so then I simplify that, and I get negative y equals x. Good thing I noticed that. Good thing I made an answer key before I even started this. Caught my mistake. So if I choose x to equal, let's just say x equals negative 1, then If I plugged in -1 in for x, then y would be equal to 1. Okay. And then my eigenvector, and I'm going to put a little 1 there, and that's going to be equal to, remember we could do alphabetical, so -1 over 1. Okay? And remember that your eigenvector can be any form of this vector. So I could have it -5 over 5, or 1 and -1, as long as it's the um, same direction. The scalar doesn't matter. So I saw somebody in class making this arrow looking like this, and it looked like a -7 or something. Just be careful with your arrow. I'm not going to say who did that, to protect the innocent. Okay, so I've got this vector that goes with eigenvalue 1. Okay, so now with eigenvalue, the second eigenvalue, we're going to find the eigenvector that goes with the second eigenvalue that's equal to 2. So matrix A is -3, -4, 5, and 6, minus 2, 0, 0, 2, and we're going to make that equal to okay, that gets me -3 minus 2, which gives me -5. -4 minus 0 is -4. 5 minus 0 is 5. And 6 minus 2 gives me 4. Okay. And so we're multiplying this by x and by y. And then that's equal to 0 and 0. Okay. So now I'm going to get my equation. So I do -5 times x, which gives me -5x. -4 times y, which gives me -4y. And then that's going to be equal to 0. Okay, so I can add 4y on both sides, and I have -5x equals 4y. And I can divide both sides by -5, and I get x equals -4/5 y. Okay, and so now I can say when y equals 1, if I made that equal to 1, then x would be equal to -4/5. Okay, and using that information, I can find my eigenvector number 2 is equal to -4/5, and the other one would be 1. And it would also be okay to say that my second eigenvector, if I could multiply this by a scalar of 5, and I could say that I could use -4 and 5 also. It doesn't matter if I use this or this, or some multiple, as long as if I multiply a scalar which multiplies both of these by the same number, that's fine. I'm going to use this because that's what Professor Dave used, and that's what I've got in my example to explain this with. So, anyways, so we've got for eigenvalue 1, we've got this eigenvector to go with it. For eigenvalue 2, I've got this eigenvector to go with it. So we're going to use that and for our next part here. Okay. So as I said before, we've got eigenvalue 1 goes with this eigenvector, and eigenvalue 2 goes with this eigenvector. Okay. Okay, so using the relationship that we did before, that they talk about on this front page. So to write my diagonalized vector, it's actually really simple. I'm just going to write the first eigenvalue 1, and then the second eigenvalue here in a diagonalized form. So the first eigenvalue goes there. Now when I'm writing my matrix X, I'm going to write the first eigenvalue that goes, sorry, eigenvector, this 2 by 2 eigenvector goes here because I put this 1 as the first eigenvalue here. The second eigenvalue that I've written is here. So since I'm using the 2 as my second eigenvalue, then I need to write this as my second eigenvalue. Okay, so I could have put the 2 here instead of the 1, but if I switched the green and the orange here, then I would switch the green and the orange columns here. And it doesn't matter if I want to use this one here and the orange one here, then I would just have these columns switched. Okay, but if the orange one here is first, then this column needs to be in that order. Okay, so now I need to find the inverse function of this. So I first need to find the determinant of this. So the determinant is equal to -1 times 1 minus 1 times -4/5, and that gets me -1 plus 4/5, which simplifies to -1/5. Okay, so that's my determinant. And so using our formula sheet, so when we're doing the inverse matrix, we have to do 1 over the determinant. So 1 divided by -1/5 times, and then the A and the D values here switch. So this -1 and the 1 switch, and then the C and the B here, they change signs. So this one here is going to become -1. This -4/5 becomes +4/5. Okay, and then so if I've got 1 divided by -1/5, that's the same thing as 5, sorry, -5 times 1/4, -1, -1, right? And so then I can just multiply the -5 times everything. And so now I can say my inverse function of this guy here is going to be equal to -5 times 1, which is -5. -5 times that gives me 4. -5 times that gives me 5. And -5 times that gives me 5. Okay. So now I've got my my inverse function. So I can write this as A equals, so X we know as -1, -4/5, 1, and 1. D, my diagonalized vector, is 1, 0, 0, 2. And my inverse vector we know is -5, 4, 5, and 5. Okay, and we can go through all these steps. I'm just going to show this here. If you want to see this done really carefully, I suggest you watch Professor Dave's explanation. He does an excellent job explaining this portion right here. The only thing that's different with his explanation is the reduced row echelon form when he explains um, this part right here. That's the only thing different that he does. Okay. Okay. Professor Dave does this one, and the check for comprehension. You have the little funny music. Doo, 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 doo. Okay, so, but then he just shows the answer, and he doesn't show any work. So I'm going to show you my work for doing this. So to figure out the eigen values, I do a minus lambda I. So I don't know if you want to hit pause. I know it's a little messy over here. Sorry about that. Okay, so a minus this gives me this, and then I find my determinant. So I do this times this minus 2 times the negative 1. FOIL this thing out, and then combine the like terms, factor it. Same process here. A is 6, negative 1, 2, 3, minus 4, 0, 0, 4. And so I'm using this first eigenvalue of 4, right? So I'm plugging in 4 in here, and then so I get 6 minus 4 gives me 2. Negative 1 minus 0 gives me negative 1. 2 minus 0 gives me 2. 3 minus 4 gives me negative 1. xy. So I do 2 times x plus negative 1 times y equals 0. Okay, ignore this. Sorry that I wrote that. Okay, so now I can subtract y on both sides, and if I know that if y is equal to 1, then x is going to be equal to a half. Okay, so there's my first. Okay, so I know I've got this value here that goes with the value of 4. Okay, go through the same process. If I've got this 5 here, then I'm going to plug in 5 instead of my eigenvalue. My eigenvalue is 5, so I'm plugging that in. And then I go through the same process, and I get my eigenvector of 1. Okay. Okay. And then I go through the determinant, and then I get this part here. Okay. Oh, all they wanted us to do is to find this, this, and this. Okay. All right. Let's talk about example 13 first, because I don't want to waste your time. And that's the one that you don't have a video for. Okay. Example 3, you can watch the video from Diagonalize a 2 by 2 matrix full process, which is here. If this link doesn't work, simply go to YouTube and type Diagonalize a 2 by 2 matrix full process, and you will see this question. But let's do example 13. Okay, find the diagonalization of this. So, just like before, we have a minus lambda I equals 0. So 1, 2, 3, 0 minus lambda 0, 0, lambda. And I get 1 minus lambda, and then 2, and then 3, and negative lambda. Okay, and that equals 0, so I'm going to find the determinant of that. So I get 1 minus lambda times negative lambda, and then minus 3 times 2 equals 0. When I find the determinant, Okay, then I multiply this out. I get negative lambda plus lambda squared minus 6. Lambda squared minus lambda minus 6 equals 0. Factor that out, and we know that I've got lambda minus 3 and lambda minus plus 2. Okay, so now I know that lambda equals negative 2, and I know that lambda equals 3. I'm going to call this one lambda 1 and this one lambda 2. Okay, so uh, so for eigenvector 1, I'm going to replace the lambda with negative 2, so I've got minus negative 2i. Okay, so I'm replacing lambda with negative 2, and I'm going to find out this eigenvector. So I've got matrix A, I've got 1, 2, 3, 0. So instead of writing minus here, I'm going to write plus because it's minus a negative, right? And so I have 2, 0, 0, 2. And I've got x and I've got y, and it equals 0, 0. Okay. All right. 1 plus 2 gives me 3. 2 plus 0 gives me 2. 3 plus 0 gives me 3. 0 plus 2 gives me 2. And then x and y, and it equals 0. Okay, now let's get our equation. 3x plus 2y equals 0. Okay, so now I'm on my way to figuring out my eigenvector. So I'm going to subtract 2y on both sides. I get 3x equals negative 2y. And then divide both sides by 3. I get x equals negative 2/3 y. And then, so when y equals 1, we know that x is going to be negative 2/3. Okay, so that means my eigenvector 1 is equal to negative 2/3 and 1. This is the same thing as negative 2 and 3, right? If I multiply the top and bottom by 3, I'm just going to write it like this because I think this is nicer to look at than the little fraction there. Okay, so with the eigenvalue of 3, we do the same process for eigenvector. We're trying to find the second eigenvector for the second eigenvalue. So minus 3i eigenvector, the second eigenvector equals 0. Okay, so matrix A, 1, 2, 3, 0, minus 3 times the identity, which is 3, 0, 0, 3. That eigenvector, I'm going to call this x and y, and then equals the 0 vector is 0 and 0. Okay, let's subtract these two matrices. So 1 minus 3 gives me negative 2. 2 minus 0 gives me 2. 3 minus 0 is 3. 0 minus 3 gives me negative 3. Okay. X and y. 0, and 0. Okay, let's get our equation. Negative 2 times x gives me negative 2x. 2 times y gives me plus 2y, and then equals 0. Okay. Let's add 2x on both sides. So I end up with 2y equals 2x if I add 2x on both sides. So then I have y equals x. So we know that when x equals 1, y equals 1. So my eigenvector is going to be 1, 1. Okay. So so now we can, from this information, we know that for an eigenvalue of negative 2, we're going to use this eigenvector. For an eigenvalue of 3, we're going to use this eigenvector. So for my diagonalization, I'm going to say I've got negative 2, 0, 0, and I'm going to have 3. So this is eigenvalue, the first one. This is my second eigenvalue. Okay. Now for matrix P, this is going to be equal to this first matrix of negative 2, 3, because this corresponds with that eigenvalue. And then the second column here is 1 and 1, because this eigenvector that I've highlighted in yellowish greenish color corresponds with the second eigenvalue, which is 3. Now if I find my inverse matrix P, first we have to find the determinant of P, which gives me negative 2 times 1 minus 3 times 1, which gives me negative 2 minus 3, which gives me negative 5. So my inverse matrix is going to be equal to 1 divided by my determinant, which is negative 1/5, times, okay, the 2 and the 1 switch places. Sorry, the negative 2 and the 1 switch places, and the 3 and the 1 change signs. Okay, I can multiply everything by 1/5 or leave it out. Let's just multiply by 1/5. So then I get my inverse matrix equals negative 1/5, 1/5, 3/5, 2/5. When you write out your matrix, you could leave it like this with it factored out like a scalar, or you can multiply it through. It really doesn't matter, okay, when you're multiplying with a scalar. Okay, so we've answered question A. They wanted you to find these 3 things. Question B says, hence write an expression for a to the 4th power. So I'm just going to show you. So a to the 4th power, so we've written matrix P, which is this first guy here. We've got our diagonal matrix to the 4th power, and we've written our inverse matrix here. And when you've got a diagonalized matrix to a 4th power, you can simply multiply each term here to that power. And that is it for this lesson. I know this one's a little longer, but there you go.